In this lesson, we're going to cover pretty much two, maybe three topics, depending on how you want to look at it. The first topic is going to be polynomial and rational inequalities. Now, we're going to handle them basically the same way, so if you want to count them as two separate topics or one, kind of up to you. The second topic we're going to get to is going to be circles. So we're going to look at graphing circles, come up with the equation of circles. With the polynomial and rational inequalities that we're going to start with, though, I did use that word inequality. So remember, we got a three-step process for solving inequalities. And those three steps are pretend like it's an equation and solve it. So ignore the inequality sign, ignore the less than or greater than, just pretend like it's an equation. Plot those solutions and any critical values. We're crossing off critical values right now, but we are going to actually discuss it in this lesson because it's going to come up with the rational inequalities. And then when we plot those, we're going to pay attention to whether we allow equality. So whether it should be an open circle or a closed circle. And then those points are going to divide our number line up into the chunks that either work or that don't work. And so our third step is figure out which ones work and which ones don't work. So let's take a look at an example of a polynomial inequality. For this very first one, we're going to sort of fumble our way through it, and then we're going to talk about the most efficient way of doing it. So if we pretend like this is an equation, so we say, let's look at this as x minus 6, x minus 4, x minus 2 equals 0, then we can use our zero factor property that says the x minus 6 could be 0, the x minus 4 could be 0, or the x minus 2 could be 0, meaning x could be 6, x could be 4, or x could be 2. So that's the end of step 1. Step 2, plot them. So we've got 2, 4, 6. The original inequality did not allow equality, so we're going to use open circles. Next, figure out what gets shaded. So let's zoom in a little bit. Over here on the left, I need to test something to the left of 2. I'm going to test x equals 0 for this chunk. For the next chunk, I'm going to test x equals 3. That's going to be a test point that's in between 2 and 4. I could test x equals 5 for that chunk because it's between 4 and 6. And I could test x equals 7 over here because that's bigger than 6. So when I test x equals 0, I'm going to get 0 minus 6 times 0 minus 4 times 0 minus 2 is greater than 0. So I'm plugging into the original. Just to be clear, I'm plugging 0 in for all the x values because 0 is my test point. And that gets me negative 6, negative 4, negative 2 is greater than 0. This gets me positive 24 times negative 2 is greater than 0, or negative 48 is greater than 0, which is a false statement. So I do not want to shade this side because that's false. But I want you to notice something. Did it matter that that was 48? Negative 1 would have been just as false. Negative 2 would have been just as false. Any negative number would have been just as false. Now I bring that up because when I want to test x equals 3, and I plug in 3 minus 6, 3 minus 4, and 3 minus 2, then maybe I don't really care what those things equal. I just care that 3 minus 6 is a negative number. 3 minus 4 is a negative number. 3 minus 2 is a positive number. And when I multiply a negative and a negative together, I get a positive. And when I multiply a positive and a positive together, I get a positive. Is a positive number going to be bigger than 0? Yes, it will. So I should shade this interval here. And if I come over to my 5 and my 6, 5 minus 6 is negative. 5 minus 4 is positive. 5 minus 2 is positive. With one negative over there, the whole thing is negative. Are negative numbers bigger than 0? No. So I don't shade it. And when I plug a 7 in for each of the x's, then all three parentheses become positive, making the whole thing positive and making this a true statement. And so this means the areas that I've shaded are from 2 to 4, as well as from 6 to infinity. That's my actual final answer to this problem. But I'm going to tell you a little shortcut too, because we had to do a lot of work over there. If we look at all the work there, all those pluses and minuses, in most cases, the shading that we get to is going to alternate. It's going to alternate yes, no, yes, no, yes, no, yes, no. So basically, instead of testing all 4 of those intervals, I could have tested one of them, the first one, the x equals 0, and then just alternated. Once I figured out that x equals 0 was a no, then it's going to go yes, no after that. The only time that's not going to happen is if one of my factors is squared or raised to some even power. So if I had x minus 6 squared or x minus 4 to the 4th power, that's when it's not going to alternate. And we'll look at an example of that in just a little bit. But I want to point that out because I want to teach you how to do this in the most efficient way possible. And that way you don't have to spend a ton of time on these. We can turn them into hopefully easy problems. So let's look at these 2 example problems and try to do them as efficiently as possible. So this first one, if we pretend like this is an equation, then any of those factors could equal 0. Meaning the first factor of x could be 0. If x minus 6 were 0, then x would be 6. If x plus 2 had been 0, then x would be negative 2. We're going to plot those 3 values on the number line of negative 2, 0, and 6. Each of these are done with open circles because the original problem did not allow equality. Now I'm going to pick a test value from one of those intervals, and I don't care which one. Because I don't care which one, I want to pick an easy value that's easy to plug in. Ideally, I'd like to plug in x equals 0. In this case, I can't plug in x equals 0 because x equals 0 is one of my border points. So instead, what I would test is I would test x equals 1. So I'm testing in this interval here between 0 and 6. So when I plug 1 in to each of the parentheses, remember that I don't really care about the value. I care about the sign. Is it positive or negative? So I have positive, negative, positive. With only one negative in there, the whole thing is negative. And so then I say, is a negative smaller than 0? And the answer is yes, that's true. So this interval should be shaded because it results in a true statement. Now if I look back to the original problem, none of those parentheses had a square on them. So this is going to alternate. Since the interval I have in yellow is a yes, the ones next to it will be no's. The next one after that will be a yes. So it goes yes, no, yes, no. It alternates. Yes, no, yes, no, yes, no. Once I know what's shaded, I can write the interval notation. It goes from negative infinity to negative 2, and then the interval from 0 to 6. And that's the actual answer that I care about. Now the other example we're going to look at the same time is really just as simple. It's just going to have fraction endpoints, but I don't really care as long as I put those fractions in the right place. I need to say 6x plus 7 could equal 0, or 7x minus 12 could equal 0, giving me negative 7/6 or 12/7. Those are ugly fractions, but I don't care where we place them as long as I place them in the correct order, meaning the smaller one is further to the left. Negative numbers are smaller than positive numbers, so there we go. They're both open circles because of the fact that the original problem did not allow equality. And so now as we look at this, we just got to pick 1 point from one of the intervals. And as I was saying on the other example there, anytime we can pick 0, let's. It's easy to plug in. 0 is in between the negative and the positive. If I plug 0 into the first parenthesis, I get 0 plus 7. That's a positive number. In the second parenthesis, 0 minus 12 is a negative number. Are negative numbers bigger than 0? No, they're not. So we're not going to shade that middle region. Now, neither of those factors up there were squared, so we are going to alternate. Yes, no, yes, no. So that means we're shading from negative infinity up to negative 7/6, and then from 12/7 to infinity. And there's our answer. So what if we have a polynomial that's not in a nice factored form like our last couple examples? Well, get it in that form. Here we have 4 terms to this, so let's factor by grouping. If I group the first 2 together, I can pull an x squared out. I can pull a negative 4 out of that guy, leaving me x plus 2. So now I can pull the x plus 2 out of the whole thing, which leaves me x squared minus 4. X squared minus 4 factors as x plus 2, x minus 2. Well, there's actually 2x plus 2's there, isn't there? So this is x plus 2 squared times x minus 2. Okay. Now I have a factor that's squared, so I'm not going to be able to use my alternating trick, but let me show you what happens here. Now that I have this in this factored form, what are the 2 values that would make this equal to 0? Negative 2 and positive 2. We're going to use closed circles this time because the inequality sign has an or equal to. Let's test the point x equals 0. Now notice what's going on here, that our first parenthesis is squared, so it doesn't even matter what I plug in. He's positive no matter what. He's being squared. Now the second parenthesis of x minus 2, if I plug a 0 in, it becomes negative 2. A positive times a negative is a negative. Are negatives smaller than 0? Why, yes, yes they are. So we're going to shade this. Now, the squared guy is what gave us negative 2. The not squared guy is what gave us positive 2. So at the positive 2 is where we will alternate. At the negative 2 is where we don't alternate. By not alternating, we mean if it was yes on the right, it's also yes on the left. If it had been no on the right, it would also be no on the left. But as I go across this point that's supposed to alternate, It was yes on the left, which means it better be no on the right. So that means the interval I'm shading is from negative infinity all the way up to positive 2. Now remember, we're not stopping off at negative 2 because that point is colored in. So we go straight through all the way across to positive 2, and there's our answers from negative infinity to 2. Now, if the alternating thing is screwing you up, if you just don't get it, you can always test all three intervals, and you should still get the right answer as well. So now we're going to talk about solving rational inequalities. And so by rational, of course, I mean fraction-like. So we're going to deal with inequalities that might have x's in the bottom. Same three steps. Pretend like it's an equation and solve it. Plot those solutions and any critical values. And notice this time we're not crossing off any critical values. This is where we want to address it. And again, we're going to pay attention to whether the original allows equality to that point. Figure out what gets shaded to step 3. So let's define what a critical value is. A critical value is any value that makes our denominator equal to 0. Now, the reason this is a critical value is something you should always have to consider. When we are solving rational equations that have x's in the bottom, remember that any answer that we got, we had to make sure it didn't make the bottom 0, that it didn't make the denominator 0. And this is because division by 0 is undefined. You're never allowed to have a 0 in the bottom. It's literally undefined, meaning we don't know what to do. Like, you can't do it. We have to avoid it at all cost. So that's why we got to look at in these problems and say, let's take any values that would make the bottom 0 and disallow them. Straight up, just say they can't be part of the answer. For that reason, we're saying they can't be part of my answer. They're always going to be open circles. So every critical value that we plot on the number line is an open circle because an open circle says this is not part of my answer. And the whole idea here of finding these critical values is to say these are values that no matter what can't happen. I can't make my bottom 0. So we're always going to use open circles for those critical values. Now the solutions to these rational inequalities are the values that will make the top equal to 0. Now that's as long as the right-hand side of the inequality is 0. And we're going to talk about that. We're going to deal with a situation where it's not that way, but we're going to deal with it by making it that way. So the top being 0 is what gives us our solutions. And those solutions might be open circles and might be closed circles. It just depends on what the original inequality was. Did we allow equality or not? But critical values are always, 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 always open circles. So let's take a look at one example of these that we'll go through a little bit slower, then we'll get a little bit faster as we get more experience with these. So as we look at a rational inequality, we're always going to look for two things: the solutions and the critical values. The critical values, remember, are what make the denominator equal to 0. The solutions are what make the numerator equal to 0. So the solution in this case is x equals 5. The critical value is x equals 6. Now the critical value will be an open circle because they always are. Critical values are always open circles. Now the solution will also be an open circle, but it's because the original inequality sign was greater than. It wasn't or equal to. So even though they're both going to be open circles, they're open circles for different reasons. So open circle, open circle. Now we need to test a point. I'm going to test x equals 0 because I like testing x equals 0 whenever possible. And here's the cool thing. Again, just look at signs. So if I plug 0 into x minus 5, I get a negative. If I plug 0 into x minus 6, I get a negative. Negative divided by a negative is a positive. Are positive numbers bigger than 0? Yes. So I'm going to shade the side that has x equals 0. Any squares up there? No. So we'll alternate. We get a no there. We get a yes there. And we get a final answer of -infinity to 5 as well as 6 to infinity. So the only new part to rational inequalities is dealing with those critical values. Whatever makes your bottom equal to 0, put an open circle there because you're never allowed to let your denominator equal 0. All right, so let's take a look at this guy. Solutions, values that make the numerator equal to 0. Critical values, values that make the denominator equal to 0. The solution in this case is x equals -1. The critical value, x equals 4. The critical value will be an open circle because always, critical values are always open circles. Your solution at x equals -1 will be a closed circle. Because of the or equal to. We're okay with us equaling -1. We want to be equal to -1. That would make this inequality true. Now let's plot those values of -1 and 4. We said 4 is an open circle. We said -1 is a closed circle. And let's test x equals 0. Notice that x equals 0 is in the middle interval because it is between -1 and 4. If I plug 0 into the top, 0 plus 1 is positive. In the bottom, 0 minus 4 is negative. A positive divided by a negative is a negative. Are negative numbers smaller than 0? Why, yes. Yes, they are. So let's shade that. We got any squares back there in that original? No? So let's alternate. My interval is from -1 included up to 4 not included. Be careful those brackets and parentheses. Make sure you got them right. Obviously, you don't want to miss points on that kind of thing. Whoa, this one looks a little more complicated. Guess what? It's not really. Basically the same steps. We're going to say, let's take a look at our solutions. Let's take a look at our critical values. Solutions are what make the top equal to 0. Critical values make the bottom equal to 0. Our solutions are going to be 2 and -2. Our critical values are going to be -1 and +4. Our critical values are going to be open circles because of always. Our solutions are going to be closed circles because the original equality had or equal to. I'm going to write the always part, but hopefully we know at this point critical values are always open circles. Now on our number line, let's plot all 4 of those values. We had -2 was the smallest. We had -1. We had 2. We had 4. 2 and -2 were both closed circles. -1 and 4 were both open circles. And now we got to worry about our shading. Let's test x equals 0 whenever possible. X equals 0 is there in between -1 and 2. I'm going to have a total of 4 parentheses here. In the upper left, 0 minus 2 is negative. In the upper right, 0 plus 2 is positive. In the lower left, 0 plus 1 is positive. And in the lower right, 0 minus 4 is negative. I have 2 negatives. 2 negatives make a positive. Are positive numbers smaller than 0? Nope. Therefore, I'm not shading this. We got any squares up there? No? Then let's alternate. It was no there in the middle, so the next one on either side is a yes. The next one on either side of that is a no. So I'm shading -2 included up to -1 not included, as well as 2 included up to 4 not included. And that's it. So even though we had 4 points that we had to plot here, it really wasn't bad because we know the alternating trick. Not too shabby. All right, so now I wanted to look at an example in which we don't have a 0 on the right-hand side. Now, if we try to do this problem as is, we lose a lot of our tricks. Now, we are only able to look at just positives and negatives because of the fact that there was a 0 on the other side. We're only allowed to talk about solutions and critical values as being the top and bottom because of the fact that there was a 0 on the other side. So not having a 0 on the other side takes away a lot of our tricks. So what I would do if I were you is I would rewrite this until we do have a 0 on the other side. So what I would do is I would start off by subtracting the 3x to the other side. Now we also don't have a single fraction on the left-hand side, which was also necessary. So the next thing that I would do is I would find a common denominator. So I would multiply by x plus 4 over x plus 4. That gets me x minus 3x times x plus 4 all over x plus 4, which I could then distribute my -3 across to get -3x squared minus 12x over x plus 4. And then I could combine like terms to get -3x squared minus 11x over x plus 4. And if I want to be a little bit tricky, I could go ahead and factor out a -x from the top, which would leave me 3x plus 11 over x plus 4. All right, so I did a whole bunch of work to get this into a pretty form. Once I get this into the pretty form, it's just as easy as any of the rest then. We're going to have solutions. We're going to have critical values. Solutions are what make the top equal to 0. Critical values are what make the bottom equal to 0. Critical value is -4. Solutions are going to be 0 and -11 thirds. Now, -11 thirds is about -3.6 repeating. Now, I point that out so we put this on the correct side on the number line. That it would go -4, then it would be -11 thirds, then it would be 0. Now my solutions were my solutions were closed because of the fact that we had an or equal to in them. My critical value is an open circle because they always are. Now I would go ahead and test x equals 1 in this case. I would always test a positive number. Don't test a negative, because if you plug a negative in, then all of a sudden you get signs everywhere. So as I plug x equals 1 in, I really have 2 parentheses on the top. I didn't write the -x in parentheses, but it really should be. So if I plug 1 into that, -x would be -1, which is a negative. If I plug 1 into 3x plus 11, it's positive, and 1 plus 4 is positive. So the whole thing's negative. Negative numbers are smaller than 0. and therefore I should shade it. I'm going to alternate, so I'm not going to shade there. I am going to shade there. I'm not going to shade there. So that I have from -4, not included, up to -11/3 included, 0 included up to infinity. And remember that your infinities are always in parentheses because they're ideas, they're not numbers. So now we're going to shift gears to talk about circles. Let's define a circle. A circle is the collection of all points x, y equidistant from a given point, hk, called the center. So this is a fancy way of saying if you want to draw a circle, you could use that tool called a compass. Because what that compass allows you to do is it allows you to put the needle into the piece of paper and get it to stick in place. You can then adjust with the wheel how far out the pencil goes and then twist it. So the given point where you put the needle is the center. The fact that we want all the points that are the same distance away is how you can change the arm length of that compass. When you take the collection of all the points, is when you spin it, you're going to say, I'm going to go through all 360 degrees here and get every point that's that far away from my center. So what I want to notice about this here is we're talking about distance. Now we had a distance formula. We didn't really worry about memorizing it so much, but this distance formula said the distance between 2 points was the square root of the difference between the x values squared plus the difference between the y values squared. So if this distance that we're talking about is the radius, and the x values are x and h, and the y values are y and k, and I decide to square both sides, then I'm going to get myself the equation of a circle. So we typically write it actually as x minus h squared plus y minus k squared equals r squared. But this is the equation of a circle where x and y are the points that are actually on the circle, hk is the center, and r is the radius. So that's what we call the equation of a circle. So with that equation of a circle, we should be able to graph a circle. That the equation was x minus h squared plus y minus k squared equals r squared. If our center is hk, then this formula tells me that my center is -1,3 in this example. If the radius squared is 9, then my radius must be 3. So if my center is at -1,3 and my radius is 3, then that's saying I want all the points that are 3 units away from that guy. So what I would do if I were you is I would go up by 3 units, down by 3 units, to the right by 3 units, and go to the left by 3 units. And then draw something that is somewhat circular-ish. Don't just connect the dots in a diamond. But give me a circle there, and that's all it takes to graph a circle. It's actually pretty straightforward and easy as long as we can identify what the center is and what the radius is. Now, some people get thrown off if we don't have an x minus something or a y minus something. If I asked you to graph x squared plus y squared equals 4, then in your head you just want to picture that as x minus 0 squared and y minus 0 squared. And that allows you to easily see that your center is actually 0, 0. If radius squared is 4, then your radius must be 2. So this tells me our center is at the origin. I'm going to go up 2, down 2, right 2, left 2, and connect the dots with something sort of circular-ish. As good as you can do freehand anyhow. There you go. It's really as simple as that. Circles shouldn't be too bad. Where things get a little bit trickier is when we're not written in the x minus h squared form. If we're not written in that form, get it in that form. That form's got perfect squares in it. So let's complete the square. So this is going to be the time that we actually have to complete the square. Every other time that we've done it, we've sort of came up with a formula around it. There's no formula this time. And we're actually going to complete the square twice in this problem. We're going to group the x's together. There's a plus in between there. And we're going to group the y's together. And we're going to throw the 2 to the other side. So we add the 2 to the other side. We're going to complete the square on the x's. So we're going to take the middle coefficient, divide by 2, and square it. Divide by 2 gets us 3. Squared is 9. Make sure to do that to both sides of the equation. We've got to stay legal here. We got to keep it balanced. So we add 9 to the left, we add 9 to the right. For the y's, divide by 2 and square it. Divide by 2 is 5. Squared is 25. And we better do that to both sides of the equation to keep it balanced. So that gives us x plus 3 squared plus y plus 5 squared equals 36. This gives us a center of -3, -5, and a radius of 6. So we can go to -3, -5, and there's our center. With a radius of 6, we go up by 6, down by 6, right by 6, left by 6, and connect the dots with something circular-ish. There you go. Now the last example we're going to do should be a fairly easy one, that we're going to be asked to find the equation of the circle. So remember that the generic form is x minus h squared plus y minus k squared equals r squared. And literally all we're going to do is plug in the information that was given to us. We were given that the x value of the center was -7. So if I subtract -7, that becomes +7. The y value of my center was 3, so I got y minus 3 squared. And my radius squared would be 100. That's literally it. If you're asked to find the equation, just plug into x minus h squared plus y minus k squared equals r squared, and there you go.